We're live. How's everybody doing? We'll get started in a minute or so. Let some people trickle in. See, we've got a few people in the chat already. Dragonite, hello. Akshat, hello there. Hello there to you as well. All right, so the plan for today is, if you look in the description, there's a PDF with an old final exam I gave. So this is the final exam I gave last year. And so the plan is to start with question 1, and we'll work our way through the end. Okay? Hello, sir. It's Jimmy from 3rd period. I used to watching this live stream in class. Oh my gosh. Okay. So, yeah, let's give it another minute or so for people to come. But that's going to be the plan. So take a look in the description for the questions. There's 20 of them. They start with limits, and we work all the way through, basic integrals. So if you have a calc test coming up, this is a good way to review. Or if you just want to hang out, right? I'm sure a few of you aren't even taking calc this semester and you just want to hang out. That's fine also. Okay. Well, as I start all my classes, anybody would like to join in on the simultaneous sip? Doesn't take much. You just got to type sip in the chat if you joined in. All right. Good stuff. All right, so let's start with question 1 and work our way through. Molly said sip. Excellent. Okay, so here's question 1. We have this graph, and we want to evaluate some limits. All right, so this is just making sure we understand how to evaluate limits using a graph. So there were 5 parts, A, B, C, D, and E. Okay. We have the limit as x goes to 1. Limit as x goes to 1 of f of x. Am I lagging a little bit? It looks like I'm lagging. The limit as x goes to 1 of f of x. So what happens? We travel along our curve on the left and say what's happening to our function there. So even though our function's not equal to 1 there, it approaches 1 from the left. So this is equal to 1. We have the limit as x goes to 2 from the right of f of x. Again, so I guess I should mark these in. This is 1, 2, 3, and 4. So when we travel along our curve coming in from the right, our function's value is 3 at 2. Okay, so these are pretty basic. C, it's the limit as x goes to 4 of f of x. Okay, coming in from the left, it's at 2. Coming in from the right, it's also at 2. So the limit as x goes to 4 of f of x is equal to 2. D, the limit as x goes to 2 of f of x. Well, coming in from the left, it would approach 2. Coming in from the right, it approaches 3, so the limit doesn't exist, right? If the left-hand limit, which is 2, does not equal the right-hand limit, then the limit doesn't exist. So we write D and E. And then last, E, f of 2. What's the function evaluated at 2? It's 2. Okay, so this one wasn't too bad. All right, so that was number 1. So far, we got a perfect score. Okay, this next one's a little tougher. So I'll write this out, and I encourage you to try these on your own. So A is the limit as x goes to 5 of 1 over x minus 1 over 5 all over x minus 5. Okay? And then B, I'll write out when we get there. So we have the limit as x goes to 5 of 1 over x minus 1 over 5 all over x minus 5. The first thing we could do is just try to plug in x equals 5, right? If we did that, we would get 0 over 0. Is it calc 1? Yeah, this is calc 1. So if we plugged in x equals 5, we'd get 0 over 0. So we have a number of methods. We could just use L'Hopital's rule to solve this. But let's kind of go with our older methods. We could get a common denominator and see if we could cancel anything out. Right, so this is equal to the limit as x goes to 5. Getting a common denominator in the numerator would be 5 minus x over 5x times 1 over x minus 5. Right, and you can see that this numerator is just negative x minus 5. L'Hopital's rule would be overkill. Yeah, but if you're nervous, right, it's a good method if you're nervous. But here we have the limit as x goes to 5. The numerator will cancel, so that's negative 1 times 5x times just 1. And now we can plug in 5, and we get negative 1 over 25. Okay. Yeah, and we would have gotten the same answer if we used L'Hopital's rule. This would have been a little bit overpowered. Okay, let's try B. Again, with these limit questions, the first thing you should do is just plug in the value and see what happens. All right, well, let me know in the chat. What's the strategy here? Here we have x squared minus 4 over x minus 2. First thing we would do is plug in 2, right? So if we plugged in 2, we would get 0 over 0. So again, we could use L'Hopital's rule. But yeah, fun maths. I like that idea. Let's factor, okay? Right, because at the time when we learned this, we didn't really know L'Hopital's rule. So the numerator is x minus 2 over x plus 2. The denominator is x minus 2. Cancel those guys out, plug in 2, and we get 4. Are there harder questions? Yeah, the test will get harder. This is still the beginning of it. You know, with a final exam, you don't want to have too many hard questions, right? You want some easy ones. Okay. Yeah, Krish got it right. So let's keep moving along. So this test was, I gave it last spring, and they had 3 hours to take the test. So you do have to go pretty quick because there are 20 questions. So it's nice that there are some easy ones. All right, so here we have a piecewise function. Okay, and so it's x squared plus 4, 2x plus 4, and x squared, x to the third minus 2x plus a. Okay, and the question is, yeah, for my final, I didn't want any hard questions. So the question is, can we make this function continuous? Okay, so can we make this function continuous? Is there a value of a that makes this function continuous? Okay, and so you might be thinking, well, let's just worry about x equals 2 when we switch from this part of the function to this part. And we'll have to do that eventually, but let's start at x equals 0, because if our function is not continuous at x equals 0, we're done, because it's automatically not continuous no matter what value of a we plug in, or we sub in. Okay, so we want to show that our function is continuous at 0, and then we'll make it continuous at 2. Okay? And so how do we show that a function is continuous at 0? We need to show that the limit as x goes to 0 from the left is equal to the limit as x goes to 0 from the right. That shows that the limit exists. Does a, yeah, we're going to solve for a. So if you want to follow along with the exact wording of the question. The questions are in the PDF, in the description. So we want to show that the limit as x goes to 0 from the left is equal to the limit as x goes to 0 from the right. Then we want to find f of 0, and then we want to show that those two numbers are the same. And then we'll do the same thing at 2. Okay, so the limit as x goes to 0 from the left of f of x is equal to, well, it's just, you would use this part to evaluate the left-hand limit. Okay, so that's 0 squared plus 4, which is 4. The limit as x goes to 0 from the right of f of x, you would use this part, right? Because you're plugging in x values that are a little bit bigger than 0, right? So you'd use this part, which is 2 times 0 plus 4, which is also equal to 4. So good, the limit as x goes to 0 equals 4. Okay, so we just showed that the limit as x goes to 0 of f of x equals 4. Good, now we want to find f of 0. Okay, f of 0, you would use this part, right? Because 0 is less than or equal to 0. Okay, and these two values are the same. So our function is continuous at 0. Now we got to do the same thing at x equals 2. Okay, so the limit as x goes to 2 from the left of f of x is equal to 2 times 2 plus 4. Which is 8. The limit as x goes to 2 from the right of f of x is equal to, well, we'd have to just plug in 2 into here, and then we'll solve for a. Okay, so that's 8 minus 4 plus a. That's 4 plus a. Okay, and we need 4 plus a to equal 8, and then we'll just solve for a. So we have a equals 4. All right, so when a equals 4, I guess we'd have to go through and just confirm that it's continuous by evaluating f of 2, but that would just be 8 minus 4 plus 4, which is 8 again, so which is what we wanted. So when a equals 4, our function is continuous. So we had to first show that it was continuous at 0, and then just make it continuous at 2 by finding the appropriate value of a. Okay, so if you have a question about continuity, you have to check that the limit is equal to the function's value. Okay, let's keep moving. All right, here's a good one. State the limit definition of the derivative, and then use it to evaluate the derivative of some function. You know, you learn all those derivative rules, right? You learn all those derivative rules kind of early on in the semester, but it is still good to know how to, do the limit definition, because sometimes you just could approximate a derivative that way. So this is number 4. Our function is f of x equals 3x squared minus x plus 1. So where's everybody tuning in from today? How long will this stream be? The stream will go until I finish, so it could be 2 hours, could be a little shorter than that. But yeah, I would expect probably an hour and a half to 2 hours. Yeah, so where's everybody tuning in from? I tried to do the earlier time so people out on the other continents could come today. Virginia. Is that, I can't see what that flag is. Is that Brazil? Okay, so we want the limit definition of the derivative, right? So that's f prime of x is equal to the limit as h goes to 0 of f of x plus h minus f of x all over h. Israel and Brazil, oh, awesome. Okay, so we want to evaluate this, the limit of this difference quotient. So let's find f of x plus h. India, is that Texas TX? Hello, Mick. Okay, f of x plus h, that's equal to, and I'll probably need more space for this one because this question's good. Thailand. 3x plus h squared minus x plus h plus 1, which we could simplify to, okay, x plus h squared. You gotta distribute it. Okay, it's not x squared plus h squared, it's 3x squared plus 2xh plus h squared, right? I know some of you are guilty of just distributing the square, that's not allowed. Okay, minus x minus h plus 1, and this is equal to 3x squared plus 6xh plus 3h squared minus x minus h plus 1. Okay, and now we want to subtract off f of x. Okay, so f of x was 3x squared minus x plus 1. So it's this whole thing, well, minus 3x squared, so we're not going to have that term. Minus x, we're not going to have that term, and the plus 1 we also won't have. So we'll just have 6xh plus 3h squared minus h. Okay, and now we want to divide by h. And then we'll evaluate the limit as h goes to 0. Okay, so let's factor out the h in the numerator. And then the question is, so we're about to finish this up. The question is, how do we check our answer, right? Once we do all this work, how do we check our answer? Okay, so the h's cancel since we're evaluating a limit, and then we can plug in h equals 0, we get 6x minus 1. Yeah, how do we check? Use the power rule. Yeah, so remember, we know all these techniques to do it quickly now. So you can check our answer by just using the power rule. So 6x, right, bring the power in front, 6x minus 1. Good. Yeah, so you got to remember, just because you're using the limit definition of the derivative doesn't mean you can't check your answer with the techniques that you know from later on. Okay, so let's keep going. Again, if you want to follow along with the questions and try them on your own, there's a PDF in the description. Finally caught a live stream. Yeah, great. I'm glad this time works for some of you. It's 9 o'clock in the morning where I am. So it's a little bit early. Okay. So this next question, number 5, is just some rapid fire derivatives. Find the derivative, don't simplify. So it's just making sure that you know all the rules. Okay, so here we have a function f of x is equal to ax over bx squared plus cx to the third. And we want f prime of x. This is a. So f prime of x, and we don't have to simplify this. 8 p.m. Oh, wow. Okay, so we have a quotient. So how do we take the derivative of a quotient? We use the quotient rule, right? So it's the bottom times the derivative of the top, which is this a, minus the top times the derivative of the bottom. And I hope I have space here, which is 2bx plus 3cx squared. Okay. And that's all over the bottom squared. Okay, so just make sure you know the quotient rule. I see Ash is in the chat. Ash is one of my #1 commenters on my YouTube videos. I think he holds the record for most hearts. Okay, so we want to just keep going. So that's A. B is we have the function f of x is equal to the cubed root of 4x times 2 plus x to the 2/5. It's 16:20 here. Oh, so afternoon. Okay, so we have our function f of x is equal to this function. We want to take its derivative. So I see the quality is going down from time to time. Is it on my side? Are people losing focus, or is it maybe the internet connection over there? How's the video quality so far today? Okay, well, while you let me know that, I'll take this derivative. All right, so we want to take the derivative of this product. So we're going to use the product rule. Quality is fine. It's a little fuzzy. It's okay. Okay, so it might be on my side. So to take the derivative here, instead of having the cubed root, it gets a little choppy sometimes. All right, well, sorry about that. It's the best we could do. Now it's clear again. Interesting, because it seems to be clear on my side. It's a little bit blurry. All right, well, if it gets too bad, then we'll just have to stop, unfortunately. But for now, let's keep going, all right? Because this is my only setup. Okay, so we want to rewrite this as 4x to the 1/3 power times 2x plus 1, 2 plus x to the 2/5, and then we can just easily use the product rule. Clear, please continue. Yeah, let's continue. Okay, so f prime of x is first times the derivative of the second. Okay, what's the derivative of this? It's 2/5. 2 plus x to the negative 3/5, right? 2/5 minus 1 is negative 3/5. Plus the derivative of the first. What's the derivative of 4x to the 1/3? It's 1/3 4x to the negative 2/3 times the derivative of the inside, which is 4, right? The Chen Lu, as my friend Dr. Payam says. You have the Chen Lu going on here, the chain rule, times the second. Okay, and again, this I would just write it out as one big line, but I don't have enough space. Where is the epic? Yeah, I should be playing music. Okay, and that's B. Let's go on to C. Let me do it here. Did any of you watch the video I just posted a couple days ago with that that limit, that crazy limit problem? I thought that was pretty cool. Okay, so here this last one is h of x is equal to x plus 1 minus to the third minus 1 over x to the third plus 2 all raised to the 8th. Okay, and we want to take the derivative. So what are we going to do? We're going to use the power rule and the chain rule and the quotient rule. Okay. Another option is we could probably do this with. No, not really. I was going to say we could probably do this with logarithmic differentiation, but we can't. I think you need some more whiteboards. I got 3 of them. Blurry again? Yeah, I'm not sure what the solution is. Oh my, Dr. Busselkovich. All right, well, I'm going to keep going. Again, if it just gets too blurry, then we'll just have to stop. It seems clear on my side. It's what's kind of frustrating. All right, let's take the derivative. H prime of x. So what do? We bring the 8 in front, drop 1 from the power. And then times the, okay, Caitlin says it's manageable. Caitlin is my student, so as long as she says it's manageable, then we're going to continue, okay, until it gets unmanageable, we'll continue. Okay, so we bring the power in front, drop 1 from the power, and then times the derivative of the inside, right? So that's what the chain rule. the chain rules. And so what's the derivative of the inside? We have to use the quotient rule here. Okay, so it's the bottom times the derivative of the top, which is 3x plus 1 squared, minus the top times the derivative of the bottom, which is 3x squared, all over the bottom squared. Okay, so that one was kind of brutal, but bring the power in front, drop 1 from the power, and then multiply by the derivative of the inside. Okay, so that's power rule, chain rule, quotient rule, all in one. Bam, blur gone. All right, good. All right, well, let's got another one. So we had a few derivatives. We got another derivative question. So we have f of theta, so here just theta is our variable, is equal to cosine of sine of theta. And we want to find f double prime. Okay, so we want to find the second derivative of this function. So how do we do that? To get the second derivative, we need the first derivative. Okay, what's the first derivative of cosine of sine of theta? Well, it's negative sine of sine of theta times the derivative of the inside. And the derivative of sine of theta is cosine theta. Okay, and then we need another derivative. And now we have a product, so we have to use the product rule. Right? Use the Chen Lu. Yeah, we're going to use the Chen Lu and the product Lu. Okay, so it's first negative sine of sine theta times the derivative of the second, which is negative sine theta, plus the derivative of the first, which is negative cosine of sine theta, times the derivative of the inside, which is cosine theta, times the second, times cosine theta. Okay, so just to recap what I did here, because I know it went a little quick. It's a product here, right? Negative sine of sine theta times cosine theta. So we use the product rule. First times the derivative of the second plus the derivative of the first, which required the chain rule again, times the second. The blur is back. Well, we'll continue. Yeah, I think part of the issue is I'm just live streaming from a laptop. I'm not sure if that's the best strategy. It's the best I have, though. Yeah, I can use a digital whiteboard. Oh, the minus and the dot are looking the same. Yeah, so, okay, I'll do like a, so these are the dots here. I don't know if you can see that at this point. Hopefully the blur will get in focus. Okay, well, I'm going to start working on the next one. So we have this relation. So this is number 7. It says it's fine. The blur comes and goes, but with the blur, you can still make it out okay. Implicit, yeah, okay, so here we have this relation. We want to find y prime, and then we want to find the equation of the tangent line at some point. Okay, yeah, so keep me updated in the chat about the status of the blur, because it looks fine to me, so I can't, unfortunately, I can't tell if it's blurry or not. All right, so we want to find y prime, and then we want to find the equation of the tangent line. You're going to watch nonetheless. Oh, thank you. Okay, so to find y prime, let's rewrite this. A good rule of thumb is just never have the square root symbol. Just always rewrite it as a power. There's almost no reason to ever have a square root symbol unless you're like typing a paper. Okay, and so we want to find y prime, so let's take the derivative of both sides. The derivative of the left-hand side is 1/2 x plus y to the negative 1/2 times the derivative of the inside, which is 1 plus y prime. And then the right-hand side, we have 4y to the third times y prime. Okay, and we want to get all the y primes together. And then we'll factor one out and then divide by what's remaining. We got 17 people here right now. This has got to be the biggest, oh, it's 7:15, but that was probably the biggest live stream I've ever had. Okay, so let's multiply this out and then we'll bring all the y primes to the left. So this is 1/2 x plus y to the negative 1/2 plus the same thing times y prime. Okay, now let's bring all the y primes together. Okay, so we'll subtract this over to the left-hand side, and we have 1/2 x plus y to the negative 1/2 is equal to negative 1/2 x plus y to the negative 1/2 y prime plus 4y to the third y prime. Factor out the y prime, so I'll just do that on this side. And then we could divide over. So we could get y prime is equal to this guy here over this guy here. Okay, and again, don't simplify. Don't waste your time simplifying. Because when you have a calculus test, your teacher is testing you on calculus. Simplifying is like algebra. Okay, so if they wanted to test you on algebra, they would give you an algebra test. Okay, and so that's y prime. The second part of the question said, find the equation of the tangent line at the point 1, 0. Okay, so we're going to plug in. So we need y prime of 1, 0, and then we can just use point slope form. Okay, so what's y prime of 1, 0? We replace every x with a 1 and y with 0. That's 1/2 times 1 to the negative 1/2 power minus 1/2, 1 plus 0, and that's 0. Okay, so this is negative 1. And so we need the equation of the tangent line. That's what the question is. Find the equation of the tangent line. So it's y minus the y component of our point is equal to our slope, x minus the x component of our point. Okay? And again, it's good here. Don't simplify. I know there's like a y minus 0. And I would give this full credit. Okay, now we got a word problem. I saw at one point that we peaked up to 18. Do you think we'll hit 20 today? That would be incredible. Okay, on to number 8. Here we have a word problem. I'm not going to, was this a slope-related rates question? Or related question? Yeah, so this was find y prime. So find the slope of the tangent line, and then find the equation of the tangent line. So that, yeah, this is number 7 if you want to see the exact wording. Number 8, we have a question about a zombie. So I'll just read the question again if you want to see it in text. Okay, while the blur is back, I'll read it. Okay. A street light is mounted on the top of a 15-foot pole. A 6-foot zombie walks away from the pole at a speed of 5 feet per second. How fast is the tip of the zombie shadow moving? Okay, I know most of you, or a good number of you here, are not American. And you probably know feet, and feet is just our lengths. You guys, it's like what you would say for meters. We say feet. Okay, so that's just a unit of length. So here we have a 15-foot pole, and we have a 6-foot zombie who's walking this way. Okay, and the question is, how fast is the tip of the shadow moving? Wow, 22 now, jeez. All right, so we have like the light coming down, and the shadow would be over here. And the question is, how fast is that moving? Okay, so let's set this up. Okay, so we have the zombie is maybe X feet away, and it's moving this way. And the shadow is Y feet away. And we want to find dy dt. Okay, so find dy dt. And then we know dx dt is that what it was, 5 feet per second? Given dx dt is 5 feet per second. Okay, so anybody have an idea? It says, Zyka says, please don't make the stream private. Yeah, the stream will be public. Once this is done, it's going to be on my channel. Okay, so if you want to watch it later, that's fine. I'll make sure it's public. Sometimes it automatically goes to unlisted, but I'll make it public. Okay, how do we solve this problem? How do we set it up? We got the drawing going. Molly says similar triangles. Yeah, let's do similar triangles. Okay, so we have, so this length here, so we have x, y, this length here would be y minus x. Right, so we have y minus x to 6 is equal to y to 15. I'm confused why x and y are horizontal. So this is like x would be the distance the zombie is from the street light. Y is the distance the shadow is from the street light. Okay, and so let's just multiply this out so we don't have fractions. So we have 15y minus 15x equals 6y, and we could simplify this a little bit more. 9y minus 15x equals 0. All right, and so this is a related rates question, so we should get some rates, and we should take some derivatives. So 9 dy dt is equal to, minus 15 dx dt is equal to 0. We know dx dt is equal to 5. So we have dy dt is equal to 15 times 5 over 9. Okay, and so that's 25. Is that right? I don't like that answer. Somebody tell me where I messed up. It feels fast. Yeah, that's what I got. 75/9. Feels fast. But we agree. I don't have the answer, so I think the second step is wrong. Short, so leg to leg is equal to leg to leg. I like that. I guess that makes sense. That's a little bit higher than 8. So maybe the shadow is going a little bit faster than the zombie. Yeah, y is not the shadow's length, but it is how fast the shadow is moving away from the wall. Okay. Yeah, the shadow. So y is the distance the tip of the shadow is from the wall, and so we're measuring how fast that's moving. If we just found this length, how fast this is moving, then you want to be capturing the fact that the zombie is walking also. So it's like the shadow speed is going to have. Yeah, I actually like this answer. The shadow speed has the zombie's speed with it, plus a little bit extra from trigonometry. Okay. So that's good. Next, we want to use a linear approximation. Use a linear approximation to approximate number 9. So use a linear approximation to approximate the cubed root of 27.012. Okay, so remember, how do we find a linear approximation? We want to, well, let's just rewrite this as f of x is equal to the cubed root of x. We want to approximate f of 27.012. So we need to find a value of x where we could easily evaluate it, like no calculator. Okay, and we called that a. So we could let a equal 27, right? Because we know f of a is just the cubed root of 27, which is 3. Okay, and to do a linear approximation, we also need the derivative. So f prime of x, again, is 1/3 x to the negative 2/3, and then we need the derivative evaluated at a, which is 27. So 1/3, 27 to the negative 2/3. Okay, and what's 1/3? Okay, 27 to the negative 2/3 is 1/9 times 1/3 is 1/27. Okay, so our linear approximation at 27 is our slope, 1/27, times x minus 27, plus f of 27, which is 3. Okay, and so we could use this to approximate the cubed root of 27.012. Okay, so here's how we do a linear approximation. So what do we need? We need we have our function, we need the derivative, we need a number that's close to what we're interested in that we can evaluate without the use of a calculator. And then, yeah, we just had this formula. Slope times x minus a plus f of a. Okay, how's the blur? I see we've lost a few people. That's okay. I'm glad you all stayed. That does not look like a 3, it looks like a 7. Which one? Here, 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 maybe. Blur is good right now. Yeah, so in that last example, I guess I just erased it. The shadow's length is y minus x. The shadow's length was y minus x. Let's draw it again. So here we had x, y minus x, and y. But the question is, how fast is the shadow moving? And I guess it wasn't clear if it's how fast is it moving from the wall or how fast is it moving from the zombie. I interpreted it as how fast is it moving from the wall. Okay, and so the distance the shadow's tip is from the wall is y. So we want to find dy dt. If you're interested in how fast is the shadow moving from the zombie, then you would want, yeah, dy minus x dt. Okay, so that was for number 8. And so people are getting 3 1/3 for this one. That sounds believable. I don't know. I don't have a calculator. So whatever this number is. Again, this would make it very clear to me that you know what you're doing. Yeah, so if you would check, it wasn't very clear how the question was worded. So I know if I was grading, I would give you credit. If you interpret it as how fast is the shadow moving from the zombie. Okay, so that, yeah, it was not very clear. Okay, let's keep going. So here we have a function f of x is equal to x to the 1/3 times 5 minus x to the third. And we have the interval 0 to 5. Okay, and we want to find absolute max and absolute min of this function on this interval. So how do we find the absolute max and absolute min values of a function on an interval? What do we need to do? Well, I'll tell you, because there's a delay in the chat. We need to find the derivative. We need to find when the derivative is 0. We need to find when the derivative is undefined. And then we also have to test the endpoints. Okay, so we need to, when the derivative is 0, when the derivative is undefined, and then also test the endpoints. Whatever the biggest value is the max, whatever the smallest value is the min. Okay, so let's find the derivative. Here we have a product, so let's use the product rule. First times the derivative of the second. Plus the derivative of the first times the second. Okay, and so let's, I'll do it on this board so there's more space. We want to rewrite our function so we can figure out when it's equal to 0 and when it's undefined. Okay, so our function is 3 or negative 3x to the 1/3 times 5 minus x squared plus 1/3x to the 2/3 5 minus x to the third. Okay, and so we want to figure out when this is 0 and we want to figure out when it's undefined. And so what we're going to do is let's get a common denominator. So let's multiply the numerator and denominator of this part over here by 3x to the 2/3. So we have minus 9x, 5 minus x squared plus 5 minus x to the third, all over 3x to the 2/3. Okay. So here's our derivative. And we want to find when this is 0. And then we also want to find when it's undefined. Okay, so this is 0. This is 0 when the numerator is 0. Okay, so this is 0 when the numerator is 0. The derivative is 0 when the numerator is 0, so we can let's factor this and solve. Okay, and so when we solve this, we get, let's clean this up. So we get x equals 0
was asking min and max of the function, not the values of x that will give the min and max. Yeah, that's correct, but we need to find what those potential values are. So we get x equals 5 and 1/2. So these are two of our critical numbers. We also have to find when the derivative is undefined. That implies that the denominator is 0. So that gives us 3x to the 2/3 equals 0, or x equals 0. Okay, so we need to evaluate our function. We need to evaluate the function at 0, 5, 1/2, and also the endpoints, which I guess were also 0 and 5. Okay, so let's evaluate f of 0. Well, that's 0. F of 1/2, that's 1/2 to the 1/3 times 5 minus 1/2 to the 3rd, and then we need f of 5, which is also just 0. Okay, so the minimum value is 0. The maximum value is whatever this number is. Okay, I mean, it's bigger than 0, but I don't know what the exact value is. All right, so to recap, how do you find an absolute max and absolute min? You find the derivative, write it as a fraction, find when the numerator is 0, find when the denominator is 0. Those give us some critical numbers, and then we have to evaluate our original function at the critical numbers. Okay, I see in the chat 72.326. Yeah, so the highest this function is going to be is that number, and the lowest is going to be 0. Okay, let's continue. I don't know which number that was because I didn't write it down. That was number 10, halfway through the test. Okay, so this next question is about the mean value theorem. So I told my students we didn't do the mean value theorem this semester. We didn't cover it. They'll get it in Calc 2. So if you're in my class, you get 2 notes. But if you're not in my class, let's talk about the mean value theorem real quick. It says the mean value theorem, this is true or false, and then justify our answer. The mean value theorem guarantees that for the function f of x equals x to the 3rd minus 9x on the interval 0 to 5, there exists a c such that f prime of c equals -6. Okay, so true or false? You'll have to leave in 40 minutes. That's fine. That's fine. Leave. When you have to leave, that's okay. So the question is, true or false? Does the mean value theorem guarantee that on this interval 0 to 5, there exists a number c such that f prime of c equals -6? So let's see. What does the mean value theorem say? It says on the interval 0 to 5, there exists a value c such that f prime of c equals f of 5 minus f of 0 all over 5 minus 0. Okay, so if this number here is -6, then we say true. If that number here is not -6, then we'll say false. Okay, and so what is this number on the right? F of 5 is 125 minus 45, which is 80. F of 0 is 0, and then over 5. This is 16. Okay, so false, right? The mean value theorem guarantees that there is some value c between 0 and 5 such that f prime of c equals 16. It says nothing about -6. Okay. And then part B is the similar question, but we have the function g of x is equal to cosine of 3x. And our interval is 0 to pi over 6. And we're checking, is there c such that g prime of c is equal to -6 over pi. Okay, so again, we want to check this same difference quotient. So the mean value theorem guarantees there's a value of c such that g prime of c is equal to g of pi over 6 minus g of 0 all over pi over 6 minus 0. Okay, and then what's g of pi over 6? That's cosine of 3 pi over 6. That's cosine of pi over 2. Cosine of pi over 2 is 0. What's g of 0? That's cosine of 0, which is 1. So we get negative 6 over pi. So yes, well, okay, you got to be careful. Is cosine of 3x continuous? Yes. Is it differentiable on an open interval? Yes. Okay, so since cosine of 3x is continuous and differentiable on this interval, the mean value theorem guarantees that there exists a number c such that g prime of c is equal to negative 6 over pi. Okay, so this one's true. All right, how's it going? Anybody still following along? Those of you who are still participating in the chat, where are you in your schooling? Are you calculus students? Have you taken calc before? Have you not taken calc and you just like calc? One thing I really struggle with is the signs of trig function, integration and derivatives. Yeah, we'll get some integrals of trig in a second, I believe. But for now, let's do number 12. Compute the limit. All right, we have the limit as x goes to infinity. Okay, we're doing a limit towards infinity. AS level done. Oh, cool. We have the limit as x goes to infinity of the square root of 4x squared minus 5x minus 2x. Okay, how do we evaluate this? What can we do to evaluate this? I'll tell you. Let's multiply by the conjugate. Okay, so let's multiply by the conjugate. Okay. And when we do that, we get our numerator is going to be 4x squared minus 5x minus 4x squared. And our denominator is this mess here. Okay? Okay, so this is equal to the limit as x goes to infinity of minus 5x over the square root of 4x squared minus 5x plus 2x. Okay, now what? Yeah, there is a square root in the denominator. I don't know if you can see it here. Okay, rationalize again. We could do L'Hopital's actually. That's a good idea. Let me show you what we could do without L'Hopital's. Okay, we can multiply the numerator and denominator by 1 over x to the highest power that appears. Okay, you might be thinking x squared is the highest power that appears, but it's inside the square root, so that's really just an x also. So let's just multiply the numerator and denominator by 1 over x and see what we get. L'Hopital's rule would work though. Okay, so when we multiply the numerator and denominator by 1 over x, we get the limit as x goes to infinity. The numerator is just -5. Yeah, or divided by x is equal. The denominator, we have the square root of 4x squared minus 5x over x plus 2. And to bring this x inside the square root, it comes as the square root of x squared. Okay, and so this will become 4 minus 5 over x inside the square root. Okay, and now we can just try to plug in infinity, whatever that means. The -5 will stay the same, 2 will stay the same. This term goes to 0. And so we have the square root of 4, which is 2 plus 2. So -5 fourths. Okay, not bad, right? That was a pretty neat question. Again, L'Hopital's rule would have worked here. So if that's what you prefer, go ahead. But yeah, it is possible to do this question without L'Hopital's rule. Yeah, so it's negative 1.25. Okay, on to number 13. So how's everybody doing so far? We're an hour into this stream. I'm shocked with the number of people that are still here. I was kind of expecting a room of 0. So far, so good. I like it. All right, it's a good test so far. Number 13. Okay, this has a little bit of writing in it, but it's going to be curve sketching. Where do you teach? I teach in Virginia, in the United States. Okay, so here we have a function, and the derivatives are given. So x squared minus 1 over 2 x plus 2 squared, f prime is 2x plus 1 over x plus 2 to the third, and f double prime is 1 minus 4x over x plus 2 to the fourth. Country roads take me home. Kind of. Okay, so there's 2 states. There's Virginia, and then west of Virginia is West Virginia. Okay, so country roads is about West Virginia. I live in Western Virginia. So kind of. I live in the western part of regular Virginia. Okay, so what do we want to do with this question? There's a bunch of parts, but we want to sketch the graph. Okay, so we want to sketch this graph. So we want to find when the function's increasing, when it's decreasing, when it's concave up, when it's concave down, and so forth. Okay. It says find asymptotes as well. We'll do that. So we need to. Oh, thanks. Physics math wizard's here. Thank you. He said great job. So we need to find when our derivative is 0. We want to find when our derivative is undefined. We need to find when our second derivative is 0. We need to find when our second derivative is undefined, and then we can use all that to sketch the graph. Okay, so if f prime of x equals 0, that implies 2x plus 1 equals 0. So we have x equals minus 1f. I don't know if you all have seen this. I posted it a few weeks ago, or maybe a month or so ago. Last year, I tried to make a viral video 7 facts needed to graph a function by hand. And it was about curve sketching. It didn't go viral, obviously, but I thought it was pretty neat. So we want to find when our derivative is equal to 0. We want to find when our derivative does not exist. Yeah, so if you haven't watched 7 facts needed to graph a function by hand, you got to watch that. Is my audio bad, or can I not hear him? My microphone's on. Can people hear me? Okay, we want to find when our derivative is 0, find when it doesn't exist. That means x plus 2 to the third equals 0, or x equals -2. Similarly with the second derivatives. Okay, and so again, x equals -2 is when our second derivative is undefined. Oh dear, what's the problem? Good luck. The blur's back. Oh, okay, well, let's keep going. Okay, so we have, let me kind of move out of the way, because what did we do so far? We found when the derivative is 0, we found when the derivative is undefined, similarly with the second derivative. Okay, so what we're going to do is we're going to take a number line and we're going to break it up. We're going to break up our number line at every single number that we found along the way. Okay, so like critical numbers, and then similarly with like the critical numbers for second derivatives. I don't think those have a name. Okay, and then we're going to check, is our function increasing, decreasing, concave up, or concave down on each of these sections of the number line. Okay, so our most negative value is -2. Okay, and so what we want to do is we need some test values, which maybe we'll pick -3, -1, 0, and 1. So that's just x value that's in each of these segments. Okay, so -3 is in this line segment, -1 is in this line segment, 0 is in this line segment, and 1 is over here. And we want to check, is our derivative positive or negative? Is our second derivative positive or negative at each of these values? Okay, so we need f prime of -3. We don't care about the value, we just care, is it positive or is it negative? Okay, and so f prime of -3, we have a negative divided by a negative. That's a positive. Okay, so our function is increasing here, and f double prime of -3 is a positive over, well, something to the fourth is going to be positive. So a positive over a positive, which is also positive. So we're increasing concave up. So that's going to look like this. Okay, so from -infinity to -2, the curve is increasing and concave up. We want to do the same thing with each of the test values. So f prime of -1, that's a negative over a positive, that's a negative. F double prime of -1 is a positive over a positive. Okay, so we're decreasing concave up. So it's this shape. So it's like the finger, you know, the shape you get with the finger and in your thumb with the shape of the L. So it's that way. Okay. Let's keep going. F prime of 0 is a positive over a positive, which is positive. F double prime of 0 is a positive over a positive, which is a positive. So increasing in concave up again. And then the last one, f prime of 1, and f double prime of 1. So f prime of 1 is a positive over a positive. F double prime of 1 is a negative over a positive. So we're increasing concave down, like that. Okay, and so now we could go ahead and graph it. Okay, just quickly using techniques from like algebra class in high school, we know that the horizontal asymptotes are going to be, it's just going to be y equals 1/2, right? It's like you just divide the leading coefficients since the power of the top is the same as the power of the bottom. So we have y equals 1/2 is going to be a horizontal asymptote, and then similarly using techniques from high school, we know x equals 2, or x equals -2, sorry, is a vertical asymptote. Okay, and so now we can just kind of put everything in. So this section here goes like this. All right, we should find the point, right? We have an x value, we don't know the y value at -1/2. So I don't have a calculator, but just estimating what the value is, when you plug in -1/2, you have -3/4 is our numerator, and then our denominator is big, so it's close to 0. Okay, so at -1/2, we have a point around here. So we should label that, but I'm not going to. And then same thing with 1/4. So does somebody want to just type in like what the y value is at x equals -1/2 and let me know in the chat? I guess I do have a calculator. I don't know, can't get it. Oh, -1/6. Okay, good, -1/6, so that's about right. -1/6, so it's down here. And then 1/4 is going to be some positive number, it's going to be maybe over here. But we can connect the dots now. Okay, so obviously on the test you would want to label the points, but I just don't have my calculator. So it comes down to here, so using this shape, it goes to here, then connecting these dots from here to there, we're in this shape. It's going to be a negative, so it's going to be down here actually. I'll really exaggerate this. Okay, and then from 1/4 to infinity, we have this shape. Okay, and so yeah, we have a vertical asymptote at x equals -2. We have a horizontal asymptote at y equals 1/2, and then we have a min. So this is a min. We have no absolute max. I mean, no local max. Yeah, so f of 1/2 is -5/54. So that's a small number. So we have a min here, and we have a point of inflection there. Okay, there's no local max. There is a local min. Okay? And so yeah, you don't need Desmos. You don't need a TI-84. You can do it by hand. Okay? Well, I like those questions. All right, let's continue. I hope you like optimization. So that's what we're going to do now. Okay. This is number 14. Moving right along. Yeah, so those of you who are in my class, this test is probably a little bit longer than what you should expect tomorrow. Right, it's going to take me like close to 2 hours, and I know how to do all the questions. So this one's probably a little bit long, but it's good practice. Okay, so a box with a square base and open top has a volume of 62,500. So let V equals 62,500 cubic centimeters. Find the dimensions to minimize the amount of material used. So minimize the surface area. What are we going to do tomorrow? Well, my students have a test tomorrow, so they're going to ace the test. So minimize surface area. Okay, so that is the question. We have, wow, yeah, don't, centimeter in the United States. I didn't write this question. So, yeah, sorry to clarify, we have a box with a square base and an open top. Okay, so here's our box. We have a square base, so I'll call it X, X, and Y. Right, because we have a square base, open top, so there's no top here. Yeah, so square base, open top. And we want to minimize the surface area, right? We want to, suppose we're making these boxes, and we don't want to buy that much material. Okay, so what's the surface area what's the surface area of this box? Ooh, I see the picture now when it shows up on the camera, and it's a pretty sad looking box. It's a little saggy over there. All right, what's the surface area of this box? Okay, I see in the comments, that's the volume. The volume is going to be x times y. So let's write that, because we need that. Surface area is x squared plus 4xy, right? We have the bottom base is x squared, and then we have 4 faces that are x times y. Okay, we want to minimize this, but we don't know how to minimize functions of 2 variables. So we have to eliminate one of these variables using this constraint. The volume is going to be 62,500 cubic centimeters. Okay, so let's solve for one of the variables. We could solve for y, right? Y is equal to 62,500 over x squared. And now we can plug that in. So our area function, which is a function of x, is equal to x squared plus 4x times 62,500 over x squared. Okay, x over x squared is just over x. Okay. So let me just do a quick check of what 62,500. I have this calculator, but I don't know how to use it. So I'm going to just turn it off. And never use it. Okay, somebody tell me what 4 times 62,500 is. What do we need? We need the derivative, right? We're going to take the derivative, set it equal to 0. So the derivative is 2x. Okay, this could be written as x to the negative 1. So 2x minus whatever that number is. Oh, that's nice. 250,000 over x squared. Okay, and we want to find when this is equal to 0. Okay, so let's set it equal to 0. So how do we set it equal to 0? We're going to need a common denominator. So 2x to the third minus 250,000 all over x squared equals 0. And so the numerator is equal to 0. Okay, and solving for x to the third, we have x to the third is equal to 125,000. And so x is equal to 50. Okay, so why don't we have to care about when the denominator is 0? Well, when the denominator is 0, that'd be x equals 0, meaning there's no volume, right? Our volume couldn't get to be 62,500. So it doesn't make sense to have one of the lengths equal to 0. Okay, so we have x equals 50. And then you can check that this is actually going to be a min by taking the second derivative and checking if it's positive. But since there's only one critical number, you could assume that this is the min. Okay, and so what are the dimensions? 50 by 50 by, and then you would plug in x equals 50 here. So y is equal to 62,500 over 2,500. Not bad, right? Optimization, they're always kind of intimidating because you have to sketch the, sketch the region or whatever we're looking at. But yeah, it's not too bad. Yeah, I mean, to a topologist, x equals 0 makes sense, but practical math, no. Yeah, exactly. We want three-dimensional volume, so we need to have some length for each of these. And that's 25. Okay, good. So 50 by 50 by 25 would be how we would minimize the surface area. Okay. Yeah, so when you have a question, if you see a word problem and it says the word maximize or minimize, that should say optimization. That's an optimization question. And what class are you all in? Yeah, well, I'm not in class anymore, but answer the scientific nerd. What class is everybody taking now? This is just Calc 1. In the fall, I'm teaching linear algebra, so we might do some linear algebra live streams if anybody's interested in that. Oh, okay, so I have a question. Where did the x cubed come from? Yeah, so what I did here was we had 2x minus this fraction. I got a common denominator. So I guess I didn't draw it perfectly. But that's even worse. But yeah, this is all one big fraction now. So that's where the finishing up electrical engineering in Sweden. Ooh, that's impressive. Yeah, so I got a common denominator. So I multiplied this by x squared over x squared. Okay, let's continue. All right. I'm in 10th grade. I'm still in 9th grade. Gosh, it is awesome. Like when I was in high school, I would have loved to watch these live streams, but they didn't really exist. So that's awesome. I'm glad you're here. Okay, so we're on number 15. Old school integration, no antiderivatives. We're going area. All right? Watch them because it's just fun. Yeah. Okay, so we want to find the area. So this is number 15. Okay, find the area under y equals x squared from 0 to 4, no no antiderivatives. So we're going to go Riemann sum. Okay, and I'm going to do a marker swap. I'm running out of markers. Okay, and I also said in the question that there's a hint or an identity that's probably useful. So we have the sum from I equals 1 to n of I squared is equal to n times n plus 1 times 2n plus 1 all over 6. Yes, so we're not going to use like the fundamental theorem of calculus. We want to do this with a limit of a Riemann sum. Okay? And so this identity is going to come into play at some point. So the sum of the first n cubes is equal to this. Okay. So what do we know? We know the area is equal to the limit as n goes to infinity of the sum from I equals 1 to n of f of x sub I delta x. Okay? So we want to evaluate this limit. Okay? So we want to evaluate this limit. Delta x is equal to b minus a over n. So 4 minus 0 over n, which is 4 over n. And my eraser doesn't really work anymore, so I gotta use paper towel. Okay. And what else? We need x sub I, the sample points. So right endpoints are typically the easiest to use. So what we do is we take our intervals 0 to 4, and we'll break it up n times. Okay, and so this first one is going to be 0 plus 4 over n. That's just 4 over n. The next one is 4 over n plus 4 over n, which is 2 times 4 over n. The next one would be 3 times 4 over n, and so forth. So x of I is I times 4 over n, or 4i over n. Okay, so our ith sample point is 4i over n. And then the function evaluated at this sample point is going to be 4i over n squared. Which is 16i squared over n squared. Okay, so we want to evaluate the limit we want to evaluate the limit as n goes to infinity of the sum from I equals 1 to n of 16i squared over n squared times, oh, so yeah, here I is just indexing the sum. This is not root negative 1. I is just, we're indexing what sample point we're looking at. So some people would use k, I guess, but I use I. Okay, so yeah, I is just indexing which sample point we're at. So the sum from I equals 1 to n of f of x of I, so 16i squared over n squared times delta x, which is 4 over n. Okay, and we want to evaluate this limit. And we know this. Okay, so we know this. Let's 16 times 4 is 64, and n squared times n is n to the third. We could pull out those constants in front of the sum. So it's the limit as n goes to infinity of 64 over n to the third times the sum from I equals 1 to n of I squared. Okay? This is equal to this. If you go on to take discrete math, you'll prove this. It's easy to prove. In fact, I plan on proving this identity using Minecraft at some point. Haven't done it yet, but it will happen. So if you want to visualize it, I'll give you a way to visualize the identity. So this is equal to the limit as n goes to infinity of 64 n to the third times n plus 1 times 2n plus 1 over 6. Right? And this limit's easy to evaluate. Okay, like what we could do, and this is how I'll do it here, just to do it kind of quickly. Let's bring the 6 over, and then I'm going to write this as n times n times n. So instead of n to the third, I'm going to write it as n times n times n. And then when we take the limit as n goes to infinity, this term will go to 1. The next product will go to 1, and the next one will go to 2. So this term goes to 2. And so this is just 128 over 6. Okay, another way to write that is 64 over 3. Okay, how do we check our answer? How do we check our answer? All right, we did all this hard work. Instinct to Wolfram alpha. No. How do we check our answer? We could just evaluate the integral, right? We could, take the integral. Yeah, let's just evaluate the integral. So the integral from 0 to 4 of x squared dx is equal to x to the third over 3, evaluated at 0 and 4, which is 64 thirds. Okay, we did it. Good job, everybody. All right. Yeah, so what's the hard part about this? The hard part is like the notation is a little bit intimidating, but the steps are pretty straightforward, right? Find what delta x is, find what x sub I is, and in general, you could use this formula for x sub I. X sub I is equal to a plus I delta x. Okay, so here a was 0. It's like the left bound, and then I is our index, and delta x we found was 4 over n. Okay, and this is for right endpoints, but right endpoints will give us the area, so might as well use them. Okay, let's continue. Only a couple more questions left, I believe. All right, here we go. Let's see if anybody can solve this. Okay, so here's an integral, and the question says evaluate the integral by interpreting it in terms of areas. Okay, so this is number 16. So using areas or geometry, evaluate the integral from -4 to 4 of 3x minus the square root of 16 minus x squared dx. Yay, morning math. Wiley is cool. Where are you tuning in from? Where is it morning? It's morning for me here, kind of, 10:30. All right, how do we evaluate this? Well, let's sketch the region and solve, and then we'll get to some like actual integrals. Okay, so let's go one part at a time. So let's go integral from -4 to 4 of 3x dx. How do we do that? Well, let's sketch the function. Let's sketch the function y equals 3x. And we want to find this area and subtract off that area. But these regions are exactly the same. So this is equal to 0. Right? The net area is 0. 10:30 p.m. Oh my God, opposite side of the world. So this net area is 0, right? We have this would be counted positively, this would be counted negatively. So when you evaluate the integral, it's 0. And now we want to evaluate this integral. Okay, and so the question is, what does this function look like? What does this function look like? It's a semicircle with radius 4. Okay, so we want to find the area of this semicircle. And so this is with radius 4. So it's pi r squared over 2. So that's pi times 16 over 2, which is 8 pi. Okay, so the answer is 0 minus 8 pi, which is negative 8 pi. Okay, so no, I mean, I don't know how many of you have taken Calc 2. This integral could be evaluated using a technique known as trig substitution. You'd use x equals 4 sine theta, but then that's a pretty hard integral still. Yeah, so drawing a picture and just using geometry is much easier. Especially if you don't know trig substitution. And it's our only hope. All right, let's continue. So that was 16. Wrapping up. So how are you all liking the live stream? Should I do more of these? Isn't there a arctan? Yeah, there is an arctan substitution as well. Should I do more of these live streams or no? Because my semester ends, I give my final on Wednesday. So then I get a grade, which is not fun. And then I post grades, and my students will be happy because they'll do well. And then I'm on summer vacation. Caitlin says very helpful. Good. Yeah, we got a few more. Yeah, some integrals. Well, I guess it's 24-hour math live stream. That'd be awesome. All right, so here we have a function y is equal to the integral from x squared to 3x plus 2 sine squared of t dt. We want to find y prime. Okay, how do we do this? Sleep's important as well. Yeah, it is. All right, so here we have this function, y is equal to this function. We want to find y prime. How do we evaluate the derivative of an integral? What theorem do we use? Anybody know? Well, there's a delay, so I'm sure somebody's typed it in. We use the fundamental theorem of calculus, and then part 1. Okay, so let's say basically the derivative of an integral is you just plug in the function and remember to use the chain rule. But we need to rewrite our function first. So we need to have a constant on the lower bound and a function as our upper bound in order to use the fundamental theorem of calculus part 1. So the way I do it is I break up the integral at 0. Okay, you can really break it up wherever you want. Okay, so I broke up our integral at 0, and we want a constant below and a function up top. And then we can, we want a constant below and a function up top, because then we can use the fundamental theorem of calculus. So let's flip this order of integration, but that comes at the cost of a negative. So negative integral from 0 to x squared So negative this integral plus the integral from 0 to 3x plus 2 of sine squared of t dt. Okay, and now to take the derivative, we just use the fundamental theorem of calculus. So y prime is equal to negative. So we replace every t with the function that's at our upper bound. So negative sine squared of x squared times the derivative of x squared. So we're still using the chain rule, right? Because we're taking the derivative, so the chain rule is going to apply. So negative sine squared of x squared times the derivative of the inside, which is 2x, plus sine squared of 3x plus 2 times the derivative of the inside. And what's the derivative of the inside? It's just 3. Okay, so what do we use the fundamental theorem of calculus part 1 here. So we take our integral, we break it up, we need to have a constant below and a function up top, and once we're in that case, we're good to use the fundamental theorem of calculus. All right, what's Ash say here? He says happy with a bunch of emojis. I'm not sure why he's happy, but that's good. All right, let's do some integrals. So I know you all love integrals, so let's do some. Okay, number 18. All right, how do we evaluate this? How do we evaluate this integral? Using calculus. Interesting. Yeah, let's separate the fractions. Okay, so we could rewrite this integral as an integral from 1 to 4 of 2 over root x. And again, let's be adults and write that as 2x to the negative 1/2. And then this is x to the 3/2. Okay, and then we can just go through and use the power rule. Yeah, see, we could potentially use u substitution here, but power rule is easier. Let's just use the power rule. Okay, so we increase the power by 1 and divide by the new power. Increase the power by 1, divide by the new power, and evaluate at the endpoints. Okay, and so we have 4x to the 1/2 plus 2x to the 5/2 over 5, evaluated at 1 and 4. And we get this. Okay, and again, this could just be typed into your calculator, whatever this value is. When I grade, I don't really look at the number, I just look at the work. And so if I saw this would be full credit. Okay, yeah, we could have tried u substitution, but I do think that would have been a bad idea. Okay, let's continue. Number 19. All right, so this is number 19. The integral of secant of x
times secant of x plus tangent of x dx. All right, how do we evaluate this? Well, let me tell you, we can distribute tangent of x. And what's the integral of secant x tan of x? That's just secant of x. I don't even learn secant in school. It's just 1 over cosine. So it's just whatever, this is like what we call 1 over cosine of x, secant of x. Okay, so yeah, this integral here is tangent of x. And this is secant of x. And then plus c, right? Don't want to forget plus c. Right, because this is an indefinite integral, so our answer should have a plus c. All right, on to number 20, the final question. I'm going to be honest with you. An hour and 45-minute live stream makes you tired. All right. Number 20. Let's see if we can do this one. So this is the integral from 0 to 4 of x over the square root of 1 plus 2x. So what are we thinking here? How are we going to evaluate this integral? I see an idea u is equal to the square root of 1 plus 2x. How about let's try something even simpler? U equals 1 plus 2x. Right, so du would be 2x dx. Oh, no, wait, it would just be 2 dx. Okay, and so this could be rewritten as integral from 0 to 4. We'll have to change the bounds. So u of 0 is 1. U of 4 is 9, right? 1 plus 2 times 4 is 9. We still have this x. And what can we do with x? We can rewrite this to say that x is equal to u minus 1 over 2. Right? And so our integral is, we can rewrite it as the integral from 1 to 9 of u minus 1 over 2 over the square root of u du. And believe it or not, that's actually easier to work with than what we started with. This is equal to the integral from 1 to 9. Let's pull the 1/2 out in front. And we have u minus 1 over root u. Okay, so how do we deal with this? How do we deal with this integral? I guess let's first, again, adults don't use the square root sign. Adults, we use the u to the 1/2. Let's break it up, and then we can integrate each one. Okay, so let's bring the 1/2 all the way in front. U over u to the 1/2 is just u to the 1/2. And negative 1 over u to the 1/2 is u to the negative 1/2. Okay. And now let's finish it off. So we have the 1/2 in front. We have u to the 3/2 over 3/2 minus u to the 1/2 over 1/2, evaluated at our endpoints. Okay, and so this is 1/2, okay, 2/3 u to the 3/2
minus 2, use the 1/2. Evaluated our endpoints. The 2's will all cancel. And so when we evaluate at 9, we have 9 to the 3/2 over 3 minus 9 to the 1/2. Minus 1/3 minus 1. Okay. And again, you can read it like this. All right, we did it. We finished the final. So I'm going to call it quits now. Thank you all for coming. I mean, it was a lot of fun. So I'm glad you all joined. I hope this was helpful for any of you who's taking calculus this semester, or if you're taking in the future. Hopefully, this is helpful. All right. Well, thanks for being here. Yeah, I'll see you later. Did I make a mistake? Hold on, pause. See, there should be, maybe, did I make a mistake possibly? Yeah. Okay, don't leave yet. What did we make a mistake? Yeah. dx, we need a 2 and a 1/2 out here. So these should all be 1/4. Okay, sorry about that. That's better. Okay, yeah, I just lost a 1/2 at the very beginning. Okay, now let's leave. All right, so see you later. Thanks for watching.